Okay, just 2 or 3 minutes. I will start then. Till now, if anyone has any doubt, you can just, uh, I mean, keep it is as it is. I will try to discuss whatever doubt you have. Yes, yes. I will obviously discuss about product topology. I understand there is some com- uh, confusion. I will obviously discuss today. Even whatever problem, if you don't understand any line of the lecture or any line of the note, you can you can ask me. I mean, just either by message or just open your mic and ask me. I will obviously discuss any type of any small doubt. You can ask me. Okay, and obviously, if you have any doubt, you just ask me because if you have doubt, better to ask that. I mean, instead of keep remaining silence. Okay. Okay. I'm starting right now. Hello everyone. My name is Milan Kumar Mal. I am a PhD scholar in the Department of Mathematics, IIT Madras, and uh, in this tutorial session, I will conduct tutorial regarding this point set topology course. And if you have any problem, you can ask me here, or you can message me directly, or you can message in the discussion forum. And I am not assuring that if you have any problem, I will come up with instant um, instant solution. Maybe I am not known everything. This is obvious that I am not known everything, but obviously I will try to fix that problem. And good evening, Vivek. I have one problem. I have one problem. Sorry, I have one doubt. Sorry, you have one doubt that I'll obviously discuss here. I think that is also regarding point set topology, sorry, product topology, hopefully. Okay. I've tried to point it out. What about your doubts? I think Vivek has doubts regarding. Huh. I think you have doubt regarding the topology in GLNR or SLNR. Okay, those things I will discuss obviously. Okay, and if you have any problem, just feel free to share here. I am not assuring that I will come up with the instant solution. Maybe not if I am not able to give solution right now or not able to keep clear your doubts right now. I will obviously come up with the next lecture. Okay, to with the best possible solution after discussing with the professor as well. Okay, but I just encourage everyone. I just want to request everyone that if you have any problem, just ask here. Okay, and one request I want to do to here that please try to register for the examination because when a course you register for just enroll for that course, it may happen that few months after 1 month you will face some another academic pressure like another exams another things, but that time you will start to avoiding this course and then you will forget, you will start to forget things, and then course will not be complete as well. Yeah, are these topologies from and how to see them as a collection of subsets? Obviously, I'll obviously discuss that. Okay, so let's start right now. Okay, um, and please register everyone for the examination. That will push you to continue the course. That will push you to study the course completely to end to go to the end of this course. Okay. Okay, so I'll just start with some what is called first some definition that will be just as a recall. Okay, today is the 30th July. 30th July. Um, tutorial first tutorial this is okay. So recall definition of a topology. Just let X be a set. The power set of X is the set of set whose elements set whose elements elements are all possible subsets of X, and it is denoted by Px. Okay, I just want to make one request. I mean, better to when you have any problem, if you don't have any option, just to write in the comment section. But if it's better to ask uh, through the voice. I mean, just open your mic and ask. That will be better. Then that will I'll understand the problem better in better way. Okay. Okay. Now, just one thing I just want to make sure what is the power set? Power set is the collection of all subsets of X. For example, when X is a set of cardinality n, cardinality means number of elements in set is n, then power set has 2 to the power n number of elements. I think that you have read somewhere else. I mean, some in 12th course or some other place. Uh, Yes, yes, yes. You can. But you can ask me in Hindi. That doesn't problem. But I have to speak in English. That's the rule. Okay. So you can ask in Hindi. I understand in that I can help. Okay. But I have to speak in English. That's the rule. I can't speak in Hindi or any other language even. Okay. So this is the definition of power set. Okay, and the topology. What the topology says is that let another definition. I just want to recall that is that topology definition. Let X be a set and let tau let tau. This is just symbol tau. Tau is a subset of this power set. This is power set. Be a subset of the power set which satisfy three basic conditions, satisfy the following three conditions, satisfy the following three conditions. One is the empty set and the full set. Empty set phi and x are in tau. That means empty set and x should be an element of tau first. Second is that if u1, u2, ur are finitely many subsets, finitely many subsets of X, which are in tau, then their intersection, then intersection of this ui I equals to 1 to r should also be belong to tau. And the third condition is that if I be an indexing set, I be any set, I be any set. This is any set. This is just an indexing set. Okay, and for each I belongs to capital I, there exists a subset ui belongs to tau. This is their exist symbol. Okay. Then intersection, then union of all those element I coming from the index set I is belongs to tau. This indexing set can be natural number like 1, 2, 3 up to I mean continue to infinity. Someone asked for infinity, but infinity is just a symbolical. Okay, infinity are not just like this is just not a natural number or not an integer. Okay, so, I mean, there is a countable infinite number of elements. Even countable infinite number of or uncountable infinite number of I can be countable, uncountable doesn't matter. But union will be belongs to union should be belongs to the tau. This is the definition of tau. And in general, X tau is called the topological space. Topological space. Sometimes just will denote. If you can discuss CSR gate questions, then it will be good. I understand that, but I can discuss only if that is related to this portion because I am bound to discuss I bound to discuss only this course material. Okay, and obviously for CSR question that question is not very the first time. Yeah, you can ask me. I'll try to discuss, uh, but better to yeah understand Neil. But if you, I mean, in general, that questions can be discussed nearly nearly to the end of the this course because those questions involved many things. I can't discuss anything which is not discussed. I mean that topic is not covered. Then I can't discuss that topic, that thing here. Okay. No, the this is the just a definition, and the example is known that if I take tau is equals to just empty set and x, then x with tau is a topological space, is a topological space, and called trivial topology. This topology tau is called that, and tau is called a topology on x called trivial topology on X. Similarly, if I take tau is equals to power set, then obviously that set contains empty set and X because the power set of X is nothing but the all collection of all subsets of X. Then X comma tau is called discrete topology. Okay, discrete topology. Discrete topology. This is a topological space and is a topological space, and tau is called a discrete topology. Tau is called discrete topology, not a discrete topology on X. Okay, here I want to make one remarks about the discrete topology. Discrete topology means something like every singleton set is a open set. Okay, here elements of the tau is called if if x comma tau is a topological space is a topological space, then elements of tau are called open set. Some of you already I mean some of you, I think most of you done real analysis course or metric space course. There is also open set. This is more or less same. Okay, but depends on the topology, which topology we are using. But okay, this is some generalization of those things. But this is also open set. But right now, don't mix that open set with this open set. They are eventually the same, but there should need some understanding. After that, you can say that okay, those open set are actually these open set for particular cases. Okay. Now, and for discrete topology, one fact is that every subset is there. For example, in discrete topology, what I am saying that PX, tau is the collection of all subsets. The collection of all subsets. That means the singleton set will be also there. So as singleton set is there, so singleton set will also be called open set. So discrete topology is something like collection of all subsets of X. Okay, and there every singleton set is open set. And if you know that, if you look at these three property, that empty set and X should be there, that is happening in X tau case situation. But also it is saying that union of any subset, union of any collection will also be an element of tau. Okay, so that means union of any collection will also be element. That means if I take finite number of elements like x1, x2, uh, these are the open set in discrete topology. But if I take union of all these things, then I will get something like x1, x2, xn, something like this. Then that will be open set. That means every subset will again be, I mean, if tau contains singleton sets, then every subset of X will also be in tau. Okay, that is what my point here. Okay, just these two definition I want to make, because to continue the first next part. And one more thing, standard topology of R and Rn, that I will just say, and then I will come to the doubts you have till now, and if you have any doubt. Okay, standard topology, standard topology on R. Okay, first I'll talk about R, and then I know the professor this thing already in content, but I just want to say. Okay, let R be the set of all integers. R is the set of all, sorry, R be the set of all real numbers, and U subset of R. Now, tau be the collection of all subsets of R. Tau be the collection of all subsets U of R, better to write U subset of R, if it satisfies the following property. If it satisfy the condition, if it satisfy if it satisfy the following condition, that is denoted star of 1. That why this is star 1, because just for symbolically R power 1, that in that sense. What star 1 says, that this is say that for every X belongs to U, there exists an epsilon greater than 0 and epsilon greater than 0, such that that epsilon should depends on the X. I mean, not in always, but in general it depends on X, such that the interval x minus epsilon, x plus epsilon should contained in U. Okay, this is the property. If tau be the collection of all subsets of U, we satisfy this property. This is the property. Okay, this is the property. This is the property. If tau satisfy this property, then uh, if tau is the collection of all subsets U, we satisfy this property, then that will form a topology. Okay, how that is form a topology, that discuss and just roughly discuss. Okay, and then tau will form a topology. Tau will form a topology. Why this will form a topology? Just for roughly, I'm just saying that clearly, if I take empty set is there, because why empty set will be there as vacuous. Later, this is called vacuous, because what is the condition? Tau will be the collection of all subsets U, if it satisfies the following property. This, if X is in U, then we have to, then there should exist an epsilon greater than 0 which satisfies this condition, right? But empty set, is there any element in empty set? There is no element in empty set. So that means this condition is satisfying vacuously. There is no element, so this condition is satisfying vacuously. Now for R will also be an element of tau, because for every element, for every X belongs to R, we can take X minus epsilon, we can take epsilon is equals to 1, and then X minus epsilon, X minus 1 comma X plus 1 is always subset of R, right? So that gives R is in tau, and this is the first condition, and first condition satisfied. So condition satisfied. Satisfied. Now the second condition, what second condition says, that finite intersection. Okay, the finite intersection says let u1 u2 dot dot u r be element of tau, and let x belongs to, I have to show that intersection of all these I ui I equals to 1 to r is again in tau. That means I need to show that if x is in intersection of I equals to 1 to r ui, then there should exist epsilon greater than 0 which satisfy this condition, right? So then that means what, that x is belongs to ui means x is belongs to ui for all I 1 to r. That means there exists an epsilon greater than 0, epsilon I greater than 0, such that x minus epsilon I comma x plus epsilon I should contained in ui. Now take epsilon is equals to minimum of this epsilon 1, epsilon 2, epsilon r. Note that why we are taking here finite intersection. Why we are taking here finite intersection, not infinite intersection? Because if I take finite intersection and this, then epsilon minimum of this epsilon 1, epsilon 2, epsilon r will also always be greater than 0. Okay, but if I take epsilon, if I take this is infinite intersection, if I take this is infinite intersection, then that is not necessarily that every epsilon greater than, I mean this epsilon minimum of, that will not be minimum, that will be infimum. Then epsilon need not be positive. Like that, I will give a counter example here just to complete to the after this. Then if epsilon is equals to this, then that imply x minus epsilon, x plus epsilon, this is always contained in u, because this x minus epsilon, x minus x plus epsilon is contained in x minus epsilon I, x plus epsilon I, and this is contained in ui. So that means this gives me that x minus epsilon, x plus epsilon is contained in intersection of all ui I equals to 1 to r. So that means it is satisfying the star condition. This is satisfying the star condition that x belongs to, for every x belongs to, there exists an epsilon greater than 0 such that this is contained in here. So as this is contained in the star condition, so remember the star condition is, the screen is visible to you.
Yes, sir, visible.
Okay. Star condition. Just remember the star condition is this one. This red block condition is star condition. Okay. For every x belongs to, there exists an epsilon greater than 0 such that interval x minus epsilon, x plus epsilon should contain here in union. Okay. So now this satisfies the star condition. So that means intersection of all ui I equals to 1 to r is contained in the tau. Okay. And similarly, if I take arbitrary union, so this satisfies the condition 2. Satisfies. Satisfies. And the condition 3 condition says that, I mean, if I want to prove the condition 3 here, what will be the condition 3? That take arbitrary union. Let I be an indexing set or arbitrary set, indexing set, and let ui I belongs to I ui such that ui is coming from the tau. Then let x belongs to this union of I belongs to I ui. That means there exists at least one I. At least one I belongs to capital I, such that um, there exists at least one I belongs to capital I, um, such that x belongs to this ui. That means there exists then there exists an epsilon greater than 0 such that x belongs to that x minus epsilon, x plus epsilon is contained in ui. Okay, x minus epsilon, x plus epsilon contained in ui. Yeah, that's true. So that means x minus epsilon, x plus epsilon is contained in union of this ui I equals to 1 to I belongs to I capital I. That means this union of ui I belongs to capital I belongs to tau. Belongs to tau. That means that's condition 3 condition, third condition is satisfied. Okay. Now, I want to do for the standard topology of R to the power n. Now, for standard topology of R to the power n, just I will discuss R2, obviously on Rn as well, standard topology of R to the power n. Here someone asked regarding some different questions. Okay, here one counter example I want to take here just before going to standard topology of R to the power n. Here one remarks I want to make that if we replace um, condition 2 of the definition of topology, or better to not writing this way. Note that for a topological space, let x tau be a topological space. Topological space. Okay, my writing is smooth or it is just getting paused, and my writing is smooth now. I mean, you are getting paused. Little lazy. Okay, smooth. Okay. Okay, let X tau be topological space. I mean, if it is little lazy, then I can rejoin from my tab. That's okay. Let's see if it is. Let X tau be topological space, and UI and IBN I be any set, and I belongs to then intersection of I belongs to I, UI need need not be need not be an element of tau provided. Okay, just to make it more emphasize, let I be be any set, and for each I belongs to capital I, UI belongs to tau, then intersection of all UI, I belongs to capital I, need not be an element of tau. Example, let R with standard topology. Then note that for any integer n belongs to natural number, minus 1 by n, sorry, not any, for any positive integer, for any positive integer n belongs to natural number, minus 1 by n belongs to the standard topology. Okay, but intersection of n belongs to natural number, minus 1 by n comma 1 by n does not belongs to the standard topology. That means I am just want to make sure that the infinite intersection, yes, it becomes zero. Obviously, it becomes this. This is, I mean, only set like this one. This is the set. I mean, only zero element is here. But the problem is zero element is here. That's why that is okay. But why that is not an subset, not an element of the standard topology? Because standard topology says that if some element is there, if some element is there, there should exist an epsilon greater than 0, such that x minus epsilon, x plus epsilon should be in the u. But if this is the set, then we can't find any epsilon. That's we can find any epsilon greater than 0. We can find any positive epsilon for which x minus epsilon, x plus epsilon can't be here. So that is the reason we can't take infinite intersection. But note that what is happening here basically, that I will just discuss why this is happening. But one more point what I want to, but if I take finite intersection, let's take n equals to 1 to r, okay, minus 1 by n, 1 by n, then that is open set, that belongs to tau. because there I can that will be basically minus 1 by r comma 1 by r. This intersection will be basically this one. Okay, so then I can take, because whatever epsilon positive I am taking here, for example, when I am trying to prove the standard topology here, I am taking epsilon is the minimum of epsilon 1, epsilon 2, epsilon r. Okay, I am here taking minimum epsilon is uh, epsilon, yeah, here epsilon is minimum of epsilon 1, epsilon 2, epsilon r. But if I take infinite number of epsilon, how to prove that 0 is only element in this intersection? That I will also prove. Don't worry, that I will also prove. And if epsilon is in minimum of epsilon 1, epsilon 2, epsilon r, then epsilon need not be positive. This epsilon, if I take infinite number of epsilon, if I take infinite number of epsilon, then that epsilon need not be positive element. Okay, so but I need a positive element. Okay, so that is the reason. Okay, here I am saying why 0 is the only element here. Here I am saying 0 is the only element here. Please discuss the product topology. Okay, just okay. Why 0 is the only element, that I am just want to say. Okay, clearly uh, note that 0 is here. I just want to know. 0 is in minus 1 by n comma 1 by n for all n belongs to the natural number, right? That means 0 is in intersection of I equals to 1 to infinity, or I belongs to natural number minus 1 by n to 1 by n. That is clear? Okay. But why there does not exist any other element? Let any other element, let some delta positive is inside the intersection. Let delta positive such that uh, I mean, what I want to say, that 0 is the only element. If 0 is not the only element, if there exists any other element, let delta delta is not is equals to 0, any other element but not 0, intersection of I equals to 1 to n minus 1 by n comma 1 by n, then what we will have, then either delta is positive or delta is negative. Let without loss of generality, let without loss of generality, delta is positive. Okay, let's delta is positive with the loss of generality. I'm taking delta is positive, but by Archimedean property, for every positive Archimedean property, for every positive delta greater than 0, there exists a natural number n naught belongs to the natural number set such that 1 by n naught is less than delta. Right, so that means minus 1 by delta naught, that means minus 1 by delta does not belongs to minus 1 by n naught comma 1 by n naught. Is it clear? First of all, this is clear because delta is something, if you look at this is the 0, this is 1 by n naught, 1 by n naught, this is minus 1 by n naught, delta is somewhere in right hand side. This can't be in between this can't be in between this, delta is somewhere here. Okay, that is what it is saying. So delta can't be here. So as delta is not here, that means this is missing one of the element. At least delta is missing one of the intersecting element. So delta can't be intersection of I equals to 1 to infinity minus 1 by n comma 1 by n, because delta is not one of them. If I take yeah, I hope it is clear. Even delta is not in 1 by n not there, we can say one more thing: delta is not in 1 by n comma 1 by n for all n greater than is equals to n naught. That is also true. Okay, delta can't be here. Okay, that is also true. So that's why only, so delta, if delta is positive, then delta is not there. Similarly, I can say that delta is negative, then delta also can't be there. So that says that 0 is the only element in intersection of minus 1 by n comma 1 by n. Okay, n is equals to 0 to n equals to 1 to infinity, not 0. N is equals to 1 to infinity. So 0 is the only element. So this set is 0. And obviously, when this set is 0, So only element is 0 here. Only element is intersection of minus 1 by n comma 1 by n is 0 here. But can I find an epsilon positive such that such that 0 minus, so this set is basically 0. Okay, better to write this way. This set is, so intersection of I belongs to natural number or n equals to 1 to infinity minus 1 by n comma 1 by n is actually only 0 set. Okay, that gives that that intersection of I equals to 1 to infinity, n equals to 1 to infinity minus 1 by n comma 1 by n is not an open set or does not belongs to tau, because if I want that set would be in tau, then I have to find an epsilon greater than 0 such that 0 minus epsilon, 0 plus epsilon should be inside of intersection of minus 1 by n comma 1 by n. But that is not happening what I have proved right now, because any this intersection can't contain any other element of 0, but this minus epsilon comma epsilon interval contains more than element other than 0, right? It contains elements other than 0. So that is what I will write right now. So why this is not an infinite intersection can't be here. Okay, so for so here what I'm saying, so if it is possible, now for 0 belongs to intersection n equals to 1 to infinity, if this is, if now if this belongs to tau, then as 0 is belongs to intersection of n equals to 1 to infinity minus 1 by n comma 1 by n, then then it should satisfy, satisfy the condition star. Then it can be element of, then it can be member of the set. It should satisfy the star condition. But note that, but if it satisfies star condition, but if there exists any epsilon positive 0 such that 0 minus epsilon, 0 plus epsilon is contained in the intersection of n equals to 1 to infinity minus 1 by n comma 1 by n, that implies that minus epsilon comma epsilon should contain in the, sorry, this is subset not contain, this is subset, but that can't happen. I just already proved this in some, I mean this is the same reason why there does not contain any other element except 0, because but few minutes ago I have proved that minus intersection of minus 1 by n comma 1 by n does not contains any other element except 0. But intersection of n equals to 1 to infinity minus 1 by n comma 1 by n does not contain any other element except 0, because similar reason that if it contains any other element, then like there, if there is any positive element, but okay, that is the reason that then that means minus epsilon comma epsilon does not belongs to the intersection of n equals to 1 to infinity minus 1 by n, and that implies that intersection of n equals to 1 to infinity minus 1 by n comma 1 by n does not belongs to tau. Why this is not belongs? Because minus epsilon comma epsilon contains element other than 0. Clear? Obviously this is contains other than 0. Okay, clear? Okay, just to make it, if this is 0, epsilon is positive, I have said. So epsilon, if it is suppose this one, and minus epsilon will be this one, so this interval should contains more than 0. Okay, this is something like plus epsilon, this is something like minus epsilon. Okay, so this is the reason that finite intersection is taken, not infinite intersection. Infinite intersection, that I mean, why infinite intersection are not taken? Because infinite intersection and will not I mean will not be able to satisfy the star condition. Okay, because what we have showed that star condition, if the star condition is satisfied, then that will form a topology. Okay, so this is something like related. Okay, now what I just want to say, the standard topology of R to the power n. Standard topology of R to the power n. Okay, I don't know, is it? Okay, just let me once just let me one disjoin and then join from this device. Just 1 minute. It is becoming some lazy, so that's why I just want to um, just a minute. Okay. If there is any internet issue, please write here, at least in message, so that uh, I can fix it. Okay. I don't know whether screen is clear. My writing is source sent to you. No, I think now it is sent to you. Okay. 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 Thank you. Thank you. Okay, now standard topology of R to the power n. Now what R to the power n says, basically I just want to make sure R to the power n is equals to something like x is equals to, I will denote x1, x2, xn, such that each xi is coming from the R. This is the R to the power n. Now I will say here the standard topology of R to the power n tau be the collection of all subsets U subset of R to the power n such that it satisfy the condition star n. What the star n condition says, this is similar, that for every epsilon greater than 0, for every x belongs to the this set U, there exists an epsilon greater than 0 such that um, such that uh, such that x belongs to b epsilon x. What this b epsilon x I am writing, subset of U. What this b epsilon x, this is equals to all x dash belongs to the R to the power n, such that all x dash belongs to the R to the power n means this x dash should be something like x1 x2, this x dash will be like x1 dash xn dash, this belongs to R to the power n, such that mod of xi dash minus xi is less than epsilon. Okay, this is the b epsilon, if I'm not wrong. Yeah, this is the b epsilon for all I equals to 1 to n. This is the epsilon. Then similarly, we can show that empty set, then uh, then tau will form a topology, from a topology on X called standard topology, and why it I will form a topology, that I will just discuss. This is called standard topology. Why it will form a topology? Why it will form a topology? That I just want to say, that first of all empty set will be there, because empty set is vacuously true, vacuously satisfying the condition, this b epsilon, for every x belongs to U, there exists an epsilon greater than 0 such that x belongs to b epsilon x subset of U. Okay, now empty set will be here, this tau, and x will also be in tau. Why x will also be in tau? This is also similar to the previous way. For every x is equals to here R to the power n, R to the power n will also be in tau, R to the power n also be in tau. Okay, just I want to say there, whether there are written X or R. Yeah, R students in Islam. So this is okay. So phi belongs to tau, and R to the power n belongs to tau. Why R to the power n belongs to tau? Because I can take any element x. Let's take any element x is equals to x1, x2, xn. This is belongs to this is belongs to the r to the power n. Okay, this is belongs to r to the power n. Then take epsilon is equals to similarly 1. Then b epsilon x will be something like all x dash, such that mod of xi dash minus xi mod less than 1. So this set always contained in r to the power n. There is no doubt. So that means x is contained in b epsilon x, which is subset of r to the power n. That shows that r to the power n is actually belongs to tau. Similarly, if I take a finite intersection, similarly I can show the other two conditions, that if I take finite intersection and if I take arbitrary union, then we can also do the same thing. Just choice of the same thing. But here one thing I want to just make sure that we can replace. Should I prove the why this one r to the power n forming topology? Sorry, why this tau forming a topology, or just I can leave it is okay, okay, okay. I think I can leave, right? Okay, I'm leaving right now. But here one thing I want to point out. What the thing is that we can replace. I think someone has asked similar type of things. We can replace b epsilon x is equals to x dash, which is equals to x1, x2, xn, such that um, mod of xi dash minus xi less than epsilon. This condition, replace this by b epsilon dash x, which is equals to, I'm just writing this dash to make notation. X dash is equals to x1 dash xn dash, such that summation of mod xi dash minus xi, or I can write this one is real number, square I equals to 1 to n whole to the power half is less than epsilon, or half less than epsilon. That is okay. I mean, I can even avoid this half also. Okay, this one less than epsilon. I can avoid this one. I mean, replace of. I mean, that means we can define standard topology. We can define standard topology. I just want to mark this one. Okay. We can define standard topology. Define standard topology on r to the power n by this way, like this way. Let tau be the collection of all subsets. Tau be the collection of all subsets u of r to the power n, such that for every x belongs to u, or such that we satisfy the condition. Okay, such that every x belongs to u, there exists an epsilon greater than 0, such that um, x belongs to b epsilon dash x. This dash means the new one, this one. B epsilon x is the old one, okay. This dash subset of u. Then that will also be the topology. But what I want to say here is that these two topology are actually same. Okay, these two topology. But I want to prove is that these two topology, that means topology corresponding to name is also same. That is called standard topology. Why? I mean, if topology is same, then name doesn't matter. Standard topology means this is I mean, standard thing. Something like, for example, standard way 0 is the middle thing, 1 is on the right hand side, and that way. Minus 1 is on left hand side. So some standard thing is usually used that way. I mean, if the topology same means what is the thing? That collection of open sets. This collection, tau is the collection of some subsets. Topology same means that collection is same. If I take x is an set, and tau1 and tau2 are to topology, that means this tau1 is actually collection of some subsets, and tau2 is also collection of some subsets of x. But the topology are same means this collection is equals to the collection of tau2. Okay, so that means they are same topology. Now when I am taking x is r to the power n, Yes, yes. Vivek, your question, if you are asking for your question, I will obviously discuss. Don't worry. Okay. Is there any other issue, Vivek?
Sir, I wanted to ask that if
Yes, yes.
B epsilon of x represents the squares in
Yes.
R2
Right, right.
and B epsilon prime represents sphere or a kind of circle
Right, right.
in
That's
the
sphere,
topology.
sphere. That is sphere. In general, it is called sphere. In two-dimensional, it is circle.
Yes.
Right, that you are
Thank you,
correct.
sir.
That why I am saying this, that there is I'll interestingly in two-dimensional I'll in two-dimensional I will discuss, and other will automatically follow the similar way. But what I just mean, the same topology means that I want to just make sure same topology means the collection of open sets. What I am taking as the collection of open sets, that is same. That is the same topology means. Just topology is nothing but the collection of open sets, sorry, collection of sets and elements of if satisfy some conditions. Topology is just nothing but the collection of subsets which satisfy some condition. What is the condition? Those three conditions. Empty set and the full set will be there first. Second is that finite intersection will be there. Second and third will be the arbitrary union should be there. Okay, but that is the collection. When two collection are same, two collection of subsets are same, then they are same topology. So when I am saying the standard topology defined by B epsilon x, I have defined. So standard topology can be defined in any of the two ways. Yes, standard topology can be defined in any of the two ways. That is correct. And why that is correct, that I will just define. That I will just prove here. Don't worry. That I will prove here. I am saying B epsilon. If I just for note, I mean for easiest way, I will just write the topology corresponding to B epsilon x and B epsilon dash x. They are same collection of open sets, the same collection of sets. Those are called open sets. Okay. Okay. That standard two topology. I am just writing two topology corresponding to. That means two topology corresponding to B epsilon x and B epsilon dash x. This is a symbolical something. There is nothing, nothing word like that topology corresponding to B epsilon. That is not right. That are same. Why? Let tau one be the topology on X with definition corresponding to B epsilon X. Okay. This is the same one, and let tau to be the topology, and let tau to be the topology on X with definition corresponding to B epsilon x. Okay, sorry, B prime epsilon x. This is the true thing. Okay, there is one proposition proved in class, that is hopefully that is in first week lecture. That proposition I want to just that proposition I want to not proposition, that mostly corollary, I think. That corollary I want to just recall, because that will be just term, that will be like. Just a minute, I just want to recall that corollary. No, not this one. Corollary, that corollary. Huh. Okay, that for before that, I want to say something like basis, I think. Okay, not without basis, I can even prove this one. Don't worry. Now, proof. Okay, just I want to here. I want to first define something. I mean, I want to first explain something. What the topology says that. For example, I am taking R2. This is the R2 space. This is the R2 in general. It is denoted. This is the x-axis. This is the y-axis. Something like that. Okay. Now taken subset. Now taken subset like this. When I will call it open set, for every element, take an arbitrary element this. If we can find an epsilon greater than 0 with B epsilon x, that means if we can find an epsilon greater than 0, this is the epsilon, this is the point x, Okay, this is the epsilon. This should be same obviously. So just epsilon is I want to make n square. I want to make n square. This is the point P. This is the epsilon distance. Okay, this is epsilon. This is epsilon. This is epsilon. This is something like mod of xi. This point is something like x1 x2, right? And this one is like x1 minus x1 prime minus x1 less than epsilon. Like this set is something like x1 dashed comma x2 dashed, such that mod of x1 dashed minus x2 dashed, mod of x1 dashed minus x1, mod of x1 dashed minus x1 less than epsilon, mod of x2 dashed minus x2 less than epsilon. This is the set. Is it clear? Because this distance, if this distance is epsilon, then that will be like this distance is epsilon, then and this middle point is x1 x2, then this box thing is actually this thing, but box is not closed actually. This is, you can see that epsilon is less than epsilon, not less than equals to. Okay, so this is the thing. But here interesting part is that always I can find an sphere or circle inside a box, and always find a box inside a circle, open, obviously open box. The intuitively, like what I want to say is that always I can find a box here, always we can find open square inside an open ball that is called ball or sphere, and we can find a open ball inside a square, inside an open square, inside an open square, inside an open square. Why I am making this statement, that I just make sure that that is very much clear. Suppose I have an open circle, right? This is the point. Suppose this is the epsilon. This is epsilon. Okay. Uh, when you will solve the problem, sir? Yeah, just after this I'll try to whatever problem you have, that I'll solve, and then next I have some problem that I mean I've managed some problem. I'll discuss those things just to make sure. These two topology I just want to define. These two are same basically. Okay. So suppose this is open basically. Okay. Suppose this is open. I'm not. This is open. Suppose this dot is something like this is something like this is not this complete. This is something like dot is there. Okay, something like this dot type of this thing is there, then we can always find an epsilon dash greater than 0, such that there exists a box inside this, uh, inside this, this is the box. Just a minute. Okay. Yeah, inside a box for epsilon dash greater than 0, this is the epsilon dash then. Okay, this will be epsilon dash. Similarly, always I will find an circle inside this box. Okay, that is some epsilon double dash radius. Okay, why how this is this is the thing which making sense. Let how I am saying that, I want to prove that. Let first prove that tau 1 is subset of tau 2. Okay, tau 1 is the topology on X with the definition corresponding to B epsilon X. Okay. Now I want to prove that tau that is there. Okay. Let U belongs to tau 1 and X belongs to tau 2. Sorry, X belongs to, sorry. I want to prove, we want to prove epsilon U belongs to tau 2. Right. I want to prove U belongs to tau 2. How I can prove that U belongs to tau 2? But that we need to find an epsilon greater than 0. But what is the tau 2 definition? We need to find an epsilon greater than 0 such that summation of x1 minus um, what is the definition of b epsilon dash? Okay, there exists that x be inside of b epsilon dash x. That is the thing. Okay, b epsilon dash or b epsilon one. I'll write this way. B epsilon b1 b dash epsilon one of x. That I want to find. Okay, okay, okay. Just I will. Okay. By definition of u belongs to tau 1, there exists an epsilon greater than 0 such that ax belongs to b epsilon of ax, which is equals to all dash x dash, okay, x1 up to xn, such that x1 dash x2 dash, such that mod of xi dash minus xi is less than epsilon for all I equals to 1 to n. This is the thing. Then that is subset of u. That is the thing. Now I want to find an epsilon dash epsilon 1. Now take epsilon 1 is equals to epsilon by, I want to let epsilon equals to that. Just now I want to find an epsilon 1. Not getting anything as I joined recently. Can you summarize what we did it till then? Okay, basically what we have done here is that first of all I have discussed, I have just recalled the definition of power set and then topological space, and then I have said the standard topology on R, standard topology on R square, and now standard topology on R to the power n, and I am just defining that standard topology of R to the power n with two different type of definition are basically same. That is what I am trying to say, and that is what I'm trying to prove. Now I need to find an epsilon greater than epsilon 1 greater than 0. I need to find an epsilon 1 greater than 0 such that b epsilon 1 dash x, which is basically collection of all those x dash, such that xi dash minus xi mod summation of I equals to 1 to n square is less than epsilon whole to the power 1 by 2 square less than epsilon. This is what I want to say. No, this is what I want to prove. Now if I take epsilon 1 is equals to epsilon by n, take epsilon 1 is equals to epsilon by n. I hope this will be okay. Yeah, that is okay. Epsilon 1 is equals to epsilon by 2n, just to make sure. Epsilon 1 equals to epsilon by 2n. Then consider b epsilon 1 dash of x. Then b epsilon 1 dash of x. Then b epsilon 1 dash of x, which is equals to basically x dash equals to x1 dash xn dash, such that mod of xi dash minus xi is less than such that mod of summation of mod xi or xi dash minus xi square I equals to 1 to n whole to the power 1 by 2 less than epsilon. How I can say this one? Let's take this one. Now claim is that b epsilon 1 dash x is actually sitting inside b epsilon x. How I can say? Let x dash belongs to b epsilon dash x. That means summation of I equals to 1 to n mod of xi dash minus xi square whole to the power 1 by 2 less than epsilon, right? Epsilon 1, not epsilon, epsilon 1, right? Yeah. Sorry, just 1 minute. I want to say, sorry, I'm doing in reverse direction. Sorry, this will come in later. Just 1 minute. X belongs to b epsilon x. Then I want to prove that there exists an epsilon. Okay, that is, I can directly take x belongs to here. So after the claim, things are not adding up. Okay, just okay. Sorry. Oh, sorry, I did not get what you were saying. After the claim, things are not adding up. Okay, I think I'm making some mistake here. Just let me clear it. Your screen is not pinned. Okay, it is not. Sorry, it was pinned. Now it is pinned. Is it in main screen now? No. Sorry, then I'll just uh, join after just 1 minute. Now it is pinned. Okay, okay. Thank you. If there is any type of problem, just let me know. This type of problem if there is. Okay. Anytime if you face any type of problem, just let me know. Okay. Okay. Now I want to find an epsilon one such that x belongs to. Now we want to find epsilon 1 such that x belongs to b epsilon 1 dash x, which is subset of b epsilon x, which is sitting inside the u. That is what I want to find. So this one is epsilon 1 is the point what I want to find here. Okay. Now take epsilon 1 is equals to n epsilon. This can be taken. Okay. I'm taking just bigger epsilon. Then, okay, if x is there, okay, no, I can take epsilon is equals to epsilon here. Okay, then let b epsilon 1 dashed x, that is equals to what it is, x dashed is equals to x1 dashed xn dashed, such that mod of such that summation of xi dashed minus xi square I equals to 1 to n whole to the power 1 by 2 less than epsilon. This is the thing. Then if then clearly x is there, clearly x is in b epsilon 1 dash x, because just if I replace x dash by x, then that will satisfy. So x is there, and if x is belongs to x dash is belongs to b epsilon dash x, that means summation of I equals to 1 to n mod of xi dash square xi square, this to the power half is less than epsilon. That means summation of I equals to 1 to n xi dashed minus xi square is less than epsilon square. That means just for each I equals to 1 to n xi square xi dashed minus xi square is less than summation of I equals to 1 to n xi dashed minus xi square, which is less than epsilon square. That means xi dashed minus xi is less than epsilon. This mod is less than epsilon. Is it clear? That means x dashed, this is for all I, that means x dash belongs to b epsilon of x. This is clear. I think this I hope this clear. I have taken b epsilon x is there, whatever b epsilon x is there. I have taken first of all what I have taken, let u be an element in tau 1. Then what is the definition of element being tau 1? There exists an epsilon greater than 0 for every x belongs to, by definition, if tau 1, if for x belongs to for x belongs to u, there exists an epsilon 1 epsilon positive such that x belongs to b epsilon x, which is given by this one. Okay, now I want to find an b epsilon 1 x which satisfy this one. Now I am taking epsilon 1 as the this. Then if b epsilon 1 defined in this way, then x belongs to b epsilon 1 automatically, and any other x dash which is in b epsilon 1 dash x, like something like this way. Okay, that summation of I equals to 1 to n xi dash minus xi square whole to the power half less than epsilon. Then summation of I equals to 1. This is this to clear automatically, just squaring on both sides. Then for each I equals to 1 to n, I will have this condition. This is always less than equals to this, less than equals to this, and then this will be less than epsilon, right? So x dash, if x dash is here, then x dash is b epsilon x. That means b epsilon 1 dash x is subset of b epsilon x. That means there exists an epsilon greater than 0 such that x belongs to b epsilon 1 dash x, which is actually subset of b epsilon x, but that is subset of u. That means I can write x belongs to b epsilon 1 dash subset of u. That means b epsilon, that means u is an open set. U belongs to tau 2, because tau definition of u being tau 2 definition is this, that there should exist, this is the definition of tau 2. Tau 2 means for that with the definition of b epsilon dash x. Okay, this happens. Okay, now conversely that implies that tau 1 is subset of tau 2, right? Now conversely, if u belongs to tau 2, then by definition, then for x belongs to u, there exists an epsilon greater than 0. This epsilon is obviously different from the previous one. Okay, just for symbolically, such that there exists x epsilon greater than 0, such that x belongs to b epsilon dash x, that is basically all those x dash x1 up to xn dash, such that summation of xi dashed minus xi square I equals to 1 to n. This is whole to the power 1 by 2 less than epsilon. This is, and this is subset of u. Now I want to find an epsilon. Let epsilon, now we want to find epsilon 1 positive, such that b epsilon 1 x is sitting inside, x should be here and sitting inside b epsilon dash x. This is, now what will be the epsilon 1? Let's take epsilon 1 is equals to epsilon by 2n. Then b epsilon 1 x is equals to all those x dash is equals to x1 dash xn dash, such that xi dash minus xi mod is less than epsilon for epsilon 1 for all I equals to 1 to up to n. Then clearly x belongs to b epsilon 1 x. If x dash belongs to b epsilon 1 x, that means mod of xi dash minus xi less than epsilon for all epsilon 1 for all I equals to 1 to n. But I want to show that x dash is also in b epsilon x, right? That means I have to show that mod of xi dash minus xi I equals to 1 to n square whole to the power 1 by 2, that is less than epsilon, that I want to show. But this is equals to summation of I equals to 1 to n. This is less than is equals to, this is, sir, if I take epsilon by 2 then it will work. No, because why it is not, it will not work, you will realize right now. Instead of epsilon by 2n, if you take epsilon, that will work in one cases when n equals to 1. When that they, in their case, that is same actually, that square and these two are same. Why I need n, that I am just making sure. We can say that mod of xi dash minus epsilon 1. Now this will be like epsilon 1 square or whole to the power 1 by 2. This will be less than, not less than equals to, this will be strictly less than. Now epsilon 1 square means summation of, this will be like epsilon square by 4n square. Okay, now whole to the power 1 by 2, and but it is summation over n. Each of them epsilon 1 is actually epsilon 1 actually epsilon by 2n. So that means it will be like summation of I equals to 1 to, okay, this will not be the same n here, just one thing. Yeah, I equals to 1 to n epsilon by 2n square, right? This is equals to this is equals to epsilon square by 4n square into n. So I need to take root n here. So this will be then epsilon square by 2n. Okay, so this will be like epsilon square by 2n into n whole to the power 1 by 2. This will be like epsilon square by 2 whole to the power 1 by 2. This will be like epsilon by 2, that is less than epsilon. why n is needed, you can see I will take run over n elements, sum of n elements. Then I have to cancel that sum n elements by something is in below. That's why I took n. Is it clear? I think someone who asked, Sandeep, is it clear? Still there will be 4 in denominator, but that doesn't matter. It will be 4, it will be 2 actually, root 2, but that is less than epsilon. I need less than epsilon. Even I mean basically I can take here epsilon by root n. Then that will be exact adjustment. But that doesn't matter. Epsilon by root 2 is less than epsilon. That is clear, na? So you can take this one. So that means what I am getting, that means there exists an that means that x belongs to b epsilon 1 x, which is subset of b epsilon x, and that is sitting inside u. That means x belongs to b epsilon 1 x subset of u. That means u is in tau 1. That is the definition of first case. So that means tau 2 is subset of tau 1. All these things, doing all this thing is basically, that means tau 1 is equals to tau 2. That means we have the same topology, same collection of subsets, right? Is it clear? First I have proved that tau 1 is subset of tau 2, and secondly tau 1 is subset of tau 2. What I am doing, that already I have mentioned earlier, but what I am doing here is that what I am doing here exactly is that this is the, suppose this is the R2. I can clearly explain you for R2. This is some set, okay, this is some u, for example, but this is open set, so this should be something like this type of things. But here in something like this type of things, open set, nothing is actually closed here. This will be something like this type of things. Now if here, by examples, for example, I have taken an element here, right? This is the x, and this is the u set, this is the x. By first definition, if u is in tau 1, first definition, that means there I will find an box, basically. How this box will be like? Square. This is not square, but okay, let's assume this is square. This means this will be like x1 x2. Here I have x1 x2, so this will be like, if this is the x1 comma x2 point. Okay, better to write little bigger box, because I want to fit. This is belongs to tau 1, so that I will have an epsilon 1. Suppose, then that means if x1 comma x2 here it is, then this one will be like epsilon, this one will be like epsilon, okay, this one will be epsilon, and this one will be epsilon. Then this one will be like something like, um, what I can say. This is the box. This is the box. I am writing b epsilon x, right? This is the box. I am writing b epsilon x1 comma x2. This is the x, our this x1 comma x2 is the x. Okay, this is the x comma x1 x. Now what I am doing here is that I want to fit an circle here. So say here I will take, this is the circle, this is the circle I will fit here. So every, suppose I have, so this is the b epsilon 1 x1 comma x2. So obviously when I can fit a circle here, by first definition, what it is says that u belongs to tau 1 means there exists an epsilon greater than 0, such that x belongs to this b epsilon 1, that is basically this box, epsilon is here, and this box is contained in this full set u, right? Now when I am when now obviously I want to change the definition to the second portion. So now I can find an epsilon like this one, for which I can find an open set like sphere. I think Vivek is saying sphere. Sphere in two-dimensional is actually circle. That is the same thing. Circle in two-dimensional and sphere in three-dimensional. This is same. So can you replace square with rectangle or triangle? Obviously that is also more general thing. We can do same type of thing, just square with rectangle, square with triangle, square with any type of thing, like even in polygonal type of thing also, not a problem. But that should be open. That should be open means here I can't write sorry. Here open will be like something like this one. This boundary point is not there. That is what I can, like this one is the replace this one. But but this type of structure is I mean not easy to define, but rectangle is something easy can be defined. We can replace this b epsilon thing by there should exist epsilon greater than 0, epsilon 2 greater than 0, such that x1 dash minus x1 should be less than epsilon 1, x2 dash minus x2 should be less than epsilon 2. Then that will be rectangle, right? But in each rectangle I can find a square. How? I will take epsilon is equals to minimum of epsilon 1, epsilon 2, right? Then I'll get that square, right? Similarly, I can fit a circle inside there. Okay, so this is that. So I can fit a circle here. So obviously the second, by the second definition, I am able to fit a circle here, which contains the point, and this one is sitting inside you. Similarly, again I can fit a uh, fit a fit a box here inside for a circle. Suppose I have given the circle with the second definition, then I can fit a box here inside, right? That will be open set, and that way. This is the way. I hope it is clear. If there is any doubt, you can ask me regarding this, because this is something very pictorial. Okay, in more dimensional this is not pictorial. In three dimensional it is obviously pictorial, but in above dimensional this is, because this our world is three dimensional, so we can't draw something beyond three dimensional easily. So this is the thing. Okay, I have done enough thing, but here I will just come with the some different type of doubts someone have along with Vivek's doubt. If you have any specific, after saying this, if you have any specific doubts, you can again mention. First doubt I want to say, Debargo's doubt. I think Debargo is not here. Share are open in standard topology. Yes, they are open. They are obviously the basis of the topology. That is called basis of the topology. Okay, that is called basis of the topology. Those are the basic things. Okay, those are the basic things. Here I want to define first Debargo's doubt. Debargo is not here. I think he will can he can see the notes. What I will share. Define the product topology so that every product topology on R to the R square as product of R usual standard topology are same. Okay, product topology and R topology are same. I think Vivek is also asking the product topology, right? Or someone asking the product topology. Product topology, what product topology says is that product topology. Product topology says is that let tau 1 and tau 2, for 2 I am just defining, tau 1, tau 2 are two topology on X. Or no, sorry, not the same. Okay, sorry. Let x comma tau x and y comma tau y are two topological space. Okay, first I need to define the basis of the topology. Okay, just I need to I know there is already there. Just to recall, basis of the topology. Basis of the topology. Just to recall basis of the topology, and then I will go to the product topology. Basis for the topology says that let tau be a topology on X. B, this is some script B, this is called B is subset of tau. Obviously tau, this can't be beyond tau. B subset of tau is called basis of the topology if it satisfies the property basis of the topology tau, basis of the topology tau, if it satisfies the property, satisfy the following property. What is the following property? Yeah, if it satisfies the following property. What is the following property? That for any subset, let U be an element of tau, and for any x belongs to U, there exists, and W, sir, is there any topology on R2 where closed rectangle is open? Yes, I can say that. I just okay, for you. I just, after this definition I can say, but that okay, that I will say that I'm just giving you example. U subset of for any x belongs to, there exist. Uh, yes. Exactly. Discrete topology is one of the example. Correct. Srikar, thanks. Thanks. Discrete topology is one of the example where. But what your question that I think who asked that question first, Sandeep. What sir? Is there any topology on R2 where the closed rectangle is open? Only the discrete topology. Only the if in R2, only R2. Okay. When I'm talking about R2, then discrete topology is the example. Because why discrete topology exam? Just to make sure that every singleton set is in discrete topology, every singleton set is open set. Every singleton set is actually element of the topology. That means they are open set by definition. So if I take the full square means suppose I just taking like x minus a square less than is equals to 1 and x minus b. For example, I'm just like this is in between something I just not properly. Okay, I'll write this after this. Just to make the definition, let tau be a topology on X. B subset of tau is called the basis of the topology tau. If it satisfies the following property, let A be a subset of T for any X belongs to there existent W belongs to the element from the basis B, such that X belongs to W, which is subset of which sitting inside U. That is what. Okay, this is the uh, this is the this is the basis of the topology. That means for a basis is the smallest collection which contains every element, something like this. Basis is the smallest collection, some small collection which also doing the same thing after taking finite after taking arbitrary union of these elements. Intuitively basis is something, some collection of subsets of X. After taking arbitrary union of these elements of basis B, I will get the full tau. Okay. So basis is something, some subsets, something smaller set, smaller collection, whose arbitrary union of elements, whose arbitrary union of arbitrary union of elements is the topology, is the main topology. Main topology, what is the topology? Okay. Basis means basis is that B subset of tau is called basis. For every element U belongs to T and X belongs to U, there I will find an W belongs to B such that X belongs to D. Now the first condition here is that property one property that also Professor Ronnie Sebastian sir already proved this. That property is that a union of all element U belongs to the basis is actually U belongs to the basis B is actually the full set X. Why this is happening? Because what it says, it says that if U is there, then there for every U belongs to there and every X belongs to there, I will find and W belongs to there. Now X is there because tau is the topology, X should be there. Then for every X belongs to X, there exists an WX belongs to B such that X belongs to WX, which is subset of U. Right now, U is here X, which is subset of X. Now for every X I belongs to X, I will get something like this. Then union of all X belongs to X belongs to B. Union of X belongs to um, X. I'll get WX, which is subset of X. But this is something like this is also contained in X is also contained here because X is always contained in WX. X is contained in WX and that is contained there. So that will say that X is equals to union of all U belongs to B, and this is obviously then union of all U belongs to B automatically because each U is subset of each U belongs to B is subset of X. Or better to write is W here. Each W belongs to B is actually subset of S. Their union can't go outside. Okay. Better to write here this one, which is subset of union W belongs to B U W, which is subset of X. Okay, this is the thing. So this gives that X is equals to union of X belongs to W belongs to B W. That is the thing. Okay. Now the product topology says that this is now to property. Now one fixed property. I'm writing it property. What property says that um, For forming an basis, tau be the topology. What is the property that, yeah, let beta be a subset of px power set x, which satisfies the following property. What property? That one is that union of all u belongs to b, u is equals to x. Second, finite intersection. If u1, u2, ur belongs to the b collection, then for every x belongs to this intersection ui, I equals to 1 to r, there exists and wx belongs to b, such that x belongs to wx, which is belongs to intersection of all ui, I equals to 1 to r. Now, now let this is something. If a b is the collection of these, okay, b is a set which has the collection of which has these two property, okay. Now what I am saying here is that let u subset of, let t be the collection of, let tau be the collection of subsets u of x which satisfies the property that if x belongs to u, then there exists and w belongs to bx, such that x belongs to w, which is subset of u. This is the thing. So then tau be the collection of this. Then one thing is that then tau is a topology. Tau will form a topology on x. Tau will form a topology on x, and called topology topology generated by B. So basically what I just trying to say is that B is a collection of subsets of X which satisfy two properties. First is that union of all those elements should be X, and secondly is that if U1, U2, UR are the elements, intersection of all, then that should satisfy that for every X belongs to intersection I equals to 1 to R UI, there should exist and WX belongs to B, such that X belongs to WS, which is contained in the intersection I equals to 1 to R WA. Now, if beta be a collection of all those sets, now tau be another collection of subsets of u, the subset of x, which satisfies this property that for every x belongs to u, I will find an element in bx, that beta, not bx. This is the beta. This is the beta, such that x belongs to w and w belongs to script beta. Yes. W belongs to script beta, not beta x. That is the thanks. W belongs to script beta such that x belongs to W and W subset of U. So for this type of collection, if I take tau be the collection of all those sets which satisfy this property, then that will form a topology. You can see the proof. If there is any problem, I can discuss that in the next tutorial. If there is a problem, is there any problem to defining? I mean, how this tau form a topology? I can skip, right? Okay. So that will form a topology. I mean, that will satisfy those three conditions, that it will empty set will be there, x will be there, and finite intersection will be there, and arbitrary union will be there, and and the topology called the topology generated by B. Okay, this is the thing. Now one thing here is that someone asks that now product topology. Now I will come to product topology. Product topology says that let x and tau x and y and tau y are two topological space, then let B be the collection of this type of sets, such that U is coming from tau x, B is coming from tau y. Just 1 minute. Collection of all those sets, then Then B will satisfy those two conditions. B will satisfy those two conditions, above these two conditions, those two condition, and the topology, generated by B by this way, that collection of all subsets of X cross Y. Okay, collection of subsets of topology generated by B, collection of subsets of X cross Y. Okay, we satisfy this type of property. Then the topology generated by B is called product topology. Note that this is subset of power set X cross Y. This is subsets of X cross Y, right? Topology, product topology on X cross Y. This is the thing. Now, uh, now R2 have standard topology. Standard topology. Also, R comma tau R have standard topology. Yep, standard topology. Then R cross R will have a R cross R will have, this is same as R square will have product topology. So now claim product topology on R square and standard topology are same. Standard topology on R square are same. So that for that reason, I will just use one. I'll just use one corollary that regarding the basis things. That I'll recall corollary. What corollary says that let X be a set, tau 1 tau 2 be two topology on X. Uh, let beta 1 and beta 2 are basis for tau 1 tau 2 respectively. Now if beta 1 is subset of tau 2 and beta 2 is subset of tau 1, that implies that tau 1 is equals to tau 2. So now what to that? Beta 1 is the basis of tau 1. Okay, that is contained in the topology of tau 2. Beta 2 is the basis of tau 2, that is contained in the topology of tau 1. Then tau 1 is equals to tau 2, that I will prove. Now here this claim I will prove. Now note that uh, the basis for the standard topology of standard topology let standard topology on R square denoted by tau s, and product topology denoted by tau p, and basis of standard topology tau s is Bs, which is equals to collection of B epsilon x, such that epsilon belongs to the real number, sorry, epsilon belongs to the R square, and epsilon is positive. Okay, B epsilon is, I can take any one, either that square one or the rectangle one, that doesn't matter. For example, I am taking a right now square one. Okay, standard topology tau s on Bs, and basis of product topology, that is already defined there. Topology tau p is bp, that is equals to u cross v, such that u is coming from the uh, tau of r, topology of the standard topology of r. Okay. Now I want to prove that first bs is contained in the tau 1, that I want to prove. First claim, one of the claim is that bs is contained tau 2, sorry, bs is contained tau 2. I have proved tau p, bs is contained tau p, product topology, tau p. First, this is claim. So bs is something like this way. Now note that b b epsilon x is contained in bs. This is the bs, right? Then b epsilon x is equals to something like x dash, which is equals to x1 x2 dash, such that mod of xi dash minus xi, this is less than epsilon, right? For all I equals to 1 and 2, this is 2, this is only 2. Okay, this can be easily written b epsilon of xi cross b epsilon of x1 and x2. It can be easily written, right? This is same, na? This means that collection of all those elements, I mean, this means that collection of all those elements xi, which is lying between xi plus epsilon, xi minus epsilon. That means I can separate for I equals to 1 and 2. This is the two thing. I can separate it or write it productly, that x1 minus all those elements, like all those x1 dash, such that x1 minus epsilon less than x1 dash less than x1 plus epsilon, this product x2 dash, such that x2 minus epsilon less than x2 dash less than x2 plus epsilon. I can write this product form. This is the full collection. Okay, if there is any problem with this, you can tell me right now, or I will, if there is a problem, I can discuss it in the next class, this one. Okay, so these two are clear. Okay, so now that means this is containing the basis of the product topology, and that is contained in the tau 2. This is clear. Now claim. So that means that b epsilon bs, standard topology, basis of the standard topology, is contained in the tau p, right? This is the tau p. Now claim that b of the product topology is contained in the tau of the standard topology. Now b of the product topology, let u cross v is this belongs to the product topology. U cross v is in the product topology, right? Basis of the product topology. That means where u belongs to the standard topology, u and v both are belong to the standard topology, where these two are belong to the standard topology. Then I want to prove that is contained in the standard topology. Okay, that is contained in the standard topology of R square. Then for every x is equals to x1 comma x2 belongs to u cross v. Sir, kindly save these notes for revision. Yeah, I will share this note, don't worry. But do attend the class. I'm not sharing, that is okay, but please do attend the class also. U cross v, if x1 belongs to there, that means x1 belongs to u and x2 belongs to v. That means they are in standard topology of R. Okay, that means there exists an epsilon greater than 0, epsilon 1 and epsilon 2 for these two. Epsilon 1 comma epsilon 2 greater than 0, such that x1 minus epsilon 1, x1 plus epsilon 1 is contained in u, and x2 minus epsilon 2, x2 plus epsilon 2, that is also contained in u. That means there exists, if I take epsilon is equals to minimum of epsilon 1 comma epsilon 2, that means xi minus epsilon 1, x1 minus, basically I'm just saying that x1 minus epsilon, x1 plus epsilon, that is contained in u, and this is v. That x2 minus epsilon comma x2 plus epsilon, that is also contained in v. These two. Okay, now I want to show is that there exists. Okay, now that means what is happening, that means mod of, that means if I take mm, that means if I take x dash is equals to x1 comma x2, x1 dash x2 dash, such that mod of x1 dash minus x1 is less than epsilon, mod of x2 dash minus x2 is less than epsilon, this set, this is sitting inside U cross V. Is it clear? What I have done, let I want to prove this one. Product topology is contained in the standard topology. Let take an element from the product of basis of the product topology, that U cross V. That is the element. That means for every x belongs to x1 comma x2, I can surely say that x1 belongs to U and x2 belongs to V. That means there exists epsilon 1, epsilon 2 positive. These two satisfy. These two satisfy because of this property that U and V are in the standard topology of R. That means individually, as U is the open set in the standard topology of R, there exists an epsilon 1 such that it will satisfy. Similarly, for x2, there will be an epsilon 2 which will satisfy this. Now, if I take epsilon equals to minimum of epsilon 1, epsilon 2, then this will satisfy the simultaneously. That means this set will be inside U tensor U cross V, because corresponding x component and corresponding x1 component and corresponding x2 component are individually inside of U. Okay, so this will satisfy, but this is actually basis of the standard topology x1 comma x2, basis of the standard topology, right? So that means there exists an epsilon greater than 0 such that for x belongs to, or x1 belongs to x2, or x is equals to x1 comma x2 belongs to U cross V, there exists an b epsilon greater than 0, such that x belongs to b epsilon x1 comma x2, which is sitting inside U cross V. So that is the definition of the standard topology. So that means U cross V is sitting inside the standard topology of the R square, right? This is the set in R square. This is the U in R square. These two are symbolically different, but this is the set in R square. Okay, so this is the thing. So that means that U cross V, that means tau of P is subset of tau of S. The last part is not clear. Okay, what last part is saying is that up to this point it is clear that B x1 x2 is equal to that. I'm just making this red one. Up to this point it is clear. Up to red, what mark I made, that is that clear? If it is not clear, please say it. I will. Okay, no problem. Up to this point it is clear. I mean the previous part. This one I will then prove again. Okay, okay, no, thanks for clarifying. Okay, so now what I want to say is that BP belongs to tau s, right? Now what means that BP belongs to tau s? I want to prove that if some element is in BP means basis of the product topology. Basis of the product topology. What is the basis of the product topology? U cross B. U is coming from the product topology of R. V is coming from the product topology of R. Right? Now, if something is in tau s, how I can prove that something is in tau s? That for every element in that set, there exists an B epsilon x1 x2 such that x should be in that way, right? Now x is here is R cross R or R square. Okay, U is here actually U cross V or old U cross V. This is the new I am saying. Now for every x belongs to U means x is equals to something like x1 comma x2. If that is there, that means x1 belongs to U, x2 belongs to V. Now U is open set in V because product topology is something like product of open sets in U and V, right? Sorry, X and Y. Product topology, how is the basis? That U cross V, U is coming from the tau X and V is coming from the tau Y. Here X and Y are same, that is R basically, right? So here product topology is same, right? So now U cross V is there. So now if x1 x2 is there, then x1 belongs to U, x2 belongs to V. Now x1 belongs to U means there exists an epsilon 1 such that x1 minus epsilon 1, x1 plus epsilon 1 subset of U. Similarly, there exists an epsilon 2 such that x2 minus epsilon 1, epsilon 2, x2 minus epsilon, x2 plus epsilon 2, that is subset of V. Now if I take epsilon is the minimum of epsilon 2, then these two satisfy simultaneously for that epsilon. Okay, now these two satisfying simultaneously means that this set is sitting inside U cross V. Is it clear now? Clear na? How this B epsilon x1 x2 sitting inside U cross V? Okay, then that is completed, because that is the way we can say that for every x, this is the point. Okay, that there exists this type of thing such that X belongs to there and that is sitting inside U cross B. That means U cross B actually the element of the topology, right? So that means if something is in that means I can say that BP is sitting inside tau S. Then using the above corollary, I can say that this is the thing. So product topology and standard topology on are same. Is it clear? If there is any doubt, because these are all very basic things. If you don't understand here, there will be create a lots of problem in further. And the standard topology on R2 are same. Okay, now I will directly come to the Vivek's doubt. Vivek, can you hear me? I mean, are you listening, right, Vivek? I hope so. Not a problem. Vivek, question is that how GLNR, what is the how one can define the standard topology on RGLNR? For example, how one can define standard topology on GLNR or SLNR or something like this. Okay, that I am saying. Let MNR be the space of, this is vector space basically, but that does not affect here, vector space of all n cross n matrices, right? Now define a map if from Mn R is the real number set going to R to the power n square. How I will define? F of Aij, this is the matrix F of Aij. Here Aij is actually n cross n matrix that is sitting inside Mn of R, right? This will be like A11 going to A1n, comma A21 going to A2n. This way AN1 going to ANN. This is the map. This is always sitting inside R to the power n square because this is n elements. This is n elements. In this way, I will go to n number of elements set. Just to like I have the matrix. This is the first row. This is the second row. In that row, this is the last row. I'm mapping like first row in the first place, second row in the second place, last row in the last place. This way I'm defining the map. So this is the map. Okay, this is the map. Now we know R to the power n square have standard topology as like how I am discussing from the beginning. Standard topology. Then define a set B is subset of all R's MNR, or like no, not this one. F inverse of U such that, okay, there here I get then F is a bijective map. This is exercise. This is not a big exercise. This is just easy exercise. Yeah, exercise. Then F is bijective map. Then it have inverse. Okay, for every subset it has inverse. Now B is equals to F inverse U such that U is in the standard topology of the R to the power n, where TS be the standard topology of R to the power n square. Okay, then I will prove. Then we will prove B satisfy the conditions of the propositions. B satisfies conditions of the propositions. Which proposition? That one is that union of element in V belongs to B. V is equals to the full space MNR. First. Second is that if U1, U2, UR or V1, V2, VR, let V1, VR are element in B, then for every x belongs to Vi, I equals to 1 to R, there exists an W belongs to B such that X belongs to W, which is subset of intersection of I equals to 1 to Vi. How I will show these two separate satisfied? First condition, look at inverse of every element. This is bijective, right? This is bijective. As union of all U belongs to tau S, U is equals to the Rn square. This is the full space, and F is bijective map, then F inverse. I just want to make a union of all this. Union of all U belongs to tau S, F inverse of U. That means union of F inverse of, that means this is the same thing at A belongs to B, A. Okay, this should be R MNR. Or even in another way, F is bijection, or okay, or in another way, as F is bijection, F inverse of the full R to the power n square set, that should be MNR. That should be, because that's the F is bijection. So that means this union, this F inverse of R to the power n, and R to the power n is an open set, and R to the power n is an open set in standard topology of R to the power n square, right? R to the power n square, sorry. R to the power n square is the standard topology of R square. That means F inverse of R to the power n square is sitting inside element of the B. That means that F inverse of R to the power n square is sitting inside union of all A belongs to B, but that can't go outside of MNR, but this is also MNR. F inverse of R to the power n square is also MNR. That means union of all A belongs to B is equals to MNR. I hope it is clear. Is it clear why union of all A belongs to B is MNR? Okay, this is the first thing. Second thing is that let V1, V2 dot Vr is belongs to B. That means Vi is equals to F inverse of Ui for some Ui belongs to the standard topology. Right. Now, if X belongs to intersection of Vi, I equals to 1 to R, that is equals to intersection of I equals to 1 to R, F inverse of Ui, that means F of X should contain in Ui intersection of all Ui, I equals to 1 to R, right? That means as U intersection of, as Ui is in the standard topology, that means finite intersection of elements also belongs to the standard topology, because that was the last condition of the being topology. Finite intersection should be there. As finite intersection is there, then as fx belongs to the intersection of all these 1 to R Ui, this is an element of the product topology, there exists and element B epsilon x, B epsilon of fx, there exists an epsilon greater than 0, there exists an epsilon greater than 0 such that B epsilon of fx, because this is the point, is fx sitting inside here, that is sitting inside intersection of I equals to 1 to n ui. Okay. Now, what I will say here is that I want to find, okay, that means x is sitting inside that f inverse of b epsilon f of x. Okay, this is the thing. Okay, b epsilon x is sitting inside f inverse of b epsilon x, but what I want to prove here is that, okay, f inverse of some such subset. Also note that note that BEFX, this is itself and is an open set, right? That means F inverse of that set should contain in the collection B. That means there exists and W is equals to F inverse of B epsilon of f of x such that x belongs to W, which is sitting inside intersection of I equals to 1 to n ui. Is it clear? I hope it is clear. I just make a little reread that first of all, why full set is union is full set, that is okay. Secondly, is that if V1, V2, Vr is the arbitrary element, let then Vi is equals to F inverse of Ui for some Ui belongs to tau s open set. Now, if is suppose X is belongs to the intersection of all Vi, intersection of all Vi, that means X is in intersection of F inverse of Ui. X is in the intersection of F inverse of Ui. That means Fx is in the intersection of all Ui. That means uh, Fx is the intersection of Ui, and intersection of Ui being the element of the standard topology, there exists B epsilon x such that X should belongs to Fx should belongs here. But this set, I don't need to do any other thing. This set itself is the element of this. That means X is inside the intersection of F inverse of B epsilon x. Okay. That means this this hello. Okay. 2 minutes. I'll just take 2 minutes and this will end. Then X inverse will be there. And sir, is there any book to study these kind of concepts? I have Munkres, but it does not cover. Okay. Okay, that doesn't matter. I am here, but Munkre is a good book. I think that is a little hard. Maybe that seems to be a little hard, but that is a very good book. You try to read that book. I think that will be better. I'm here now. If any further discussion further explanation need, then I'm here. You can ask me. Don't worry. Okay. So this is I hope this is clear. I can take this is the W. Okay, this is the W. Then this one is automatically sitting inside here, no? Because this one is sitting inside. This one is sitting inside here. B inverse F inverse of this is sitting inside here. So this is I think this is clear. Okay. So so beta is okay. Thanks, Vivek. I think this is I'm doing for this is you because that was your doubt. So it's my duty that it is clear to you at least. So beta is satisfying the property of being satisfy the property of being the basis. Property of being the basis. Okay. Now just 2 minutes more. Okay. Now any topology not any topology generated by this beta. Now topology generated by beta is called standard topology. Standard topology of MNR. Not to be that I have obtained standard topology of MNR out of the standard topology of R to the power n square. Okay. Now I come to exact your question of Vivek that now you know there is subspace topology. Vivek, do you know there is subspace topology? Okay. What subspace topology says is that for any subset of x of so for any subset y of x and x tau be a topological space, this need not be subspace. This is just subset. Y is a subset of x tau be a topological space, then subspace topology of y. Subspace. This is called subspace topology, but y need not be subspace. Make sure y need not be subspace to define the subspace topology. Then subspace topology of y is actually u intersection of y. U is coming from the topology tau. This is the subspace topology of y. X is in set.
Yes.
X is in set and tau be a topology on that. Y is a subspace. Now, what is the subspace topology of y? That is basically u intersection of y for all u belongs to tau. This collection will form a topology. This is I'm writing tau x, tau y. Then this collection will form a topology. Will form a topology. called subspace topology. Now, GLNR. GLNR, I'm not defining definition, exact definition. You can see somewhere. SLNR or whatever related to NR is a subset of MNR. Then we can define subspace topology of GLNR or SLNR using from the main topology from subspace topology as subset of as subset of MNR with standard topology. Vivek, is it clear now? Just at least write in. If you're not able to say anything, but you can write in message. Is it clear? Okay. Thanks, Sandeep. Okay. If it is still there is any doubt, I will come with the next day. Not a problem. But today I will be do up to this point. And if till now is there any problem, is there any doubt, please. Yeah, I hope you enjoy it and please um, make sure that you join. Vivek, is it clear or doubt here? Please. Not clear? Clear to me. Okay, okay. At least it should be clear to you because that was your doubt mainly. How subspace topology? First, I am defining standard topology on MNR. Then I am just saying that how subspace topology is defined on a subset. Note that SLNR is not a subspace of MNR, but still we can define because subspace topology is defined on a subset, not on subspace. Okay. Okay. So still till now, is there any other doubt? Uh,
Sir,
is there any doubt?
sir,
Yes. Sandeep, is there any
सर
doubt?
कुछ प्रॉब्लम सॉल्व सर कुछ प्रॉब्लम सॉल्व करवाएं क्या इनके अलावा सर नोट्स के अलावा
I will do that. I will do that in the next class. I will try to do that. I have also
तो जो
prepared for
ये
some
उनको
problem,
सर
but time does not allow me right now because my term is supposed to be
सर ये
end at 9.
कॉन्सेप्ट
Yes.
सर नोट से भी कॉन्सेप्ट पढ़ लेते हैं पर यदि आप कुछ अलग से करवाएं तो इंटरेस्टिंग हो जाएगी
कुछ problem हो जाए तो interesting होगा.
यस सर यस
Okay, okay. We will obviously discuss problem. Don't worry. We can do that in the next session, and also we will try to discuss some problem regarding assignment. But after assignment completion, when assignment last date,
यस
after that I will discuss the assignment. Otherwise, I can give a hint of assignment, but I will not allow to give the assignment solution. Okay, so before asking any question from assignment, just make sure that you will not get solution here, but don't be disappointed because I'm not allowed to give solution, but I can give you a hint. And after the completion, after the date of assignment completion, I will discuss the full assignment, that
यस
assignment. Okay, and I'll try to cover more problem in the next. Please make sure that you have raised your doubts in the discussion forum or in class also. Okay.
यस
Okay, we'll continue from the next day. Okay, thank
यस
you. Thank
थैंक
you.
यू
I'll stop here. Okay. Yeah, okay. Kidney cells means Ronnie sir. Okay. Ronnie sir, right? Vivek? Are
Yes,
you
sir.
talking?
Ronnie, sir, actually.
Okay, okay. That I can't say do anything. What type of problem you are facing?
Sir, I feel like he's going too far ahead and I am lagging behind.
Okay. Mm, okay. What should I say? You have to spend time there. I think that's the only thing I can say. Uh, you have to spend a little more time. That's what I think. Okay. Okay. Sorry.
सर कोई बुक सर और रिकमेंड कर दीजिए सर इंक्रीज के लिए
Any book that is Mooncraze is a good book, and you can follow right now. Uh, you can follow.
सर इजी
Sorry,
लगे इजी लगे
you can follow right now the SAR's note. Okay. you can follow the shar's note, and that will be, I think that will be enough. Don't worry, I'm just asking, just requesting everyone that please register for the exam, because if you don't register for the exam, you will start to avoid lectures, you will start to avoid those things, this tutorial, and then you will not, at the end of the semester, you will not be able to complete the course, and you will be like in halfway of the course, and that will not be fruitful to you. Okay. Okay, I think if you don't have any doubt and Vivek, I will suggest you that you just spend a little more time. Try to see the video, just just to make sure that you backward 10 seconds and try to read, and you try to read lecture notes as well. I think that would be a better. Otherwise, I am here. If any doubt, if you have, you can just ask me here. Even in any proof in Ronnie sir proof, there is you are not able to understand, you can ask her. Okay. Okay, I'll stop here. Okay.
सर सर
Thank you.
सर हेलो सर
Yes, yes, Sandeep.
सर CSIR के लिए सर कुछ हिंट देंगे कैसे प्रिपेयर करें उसके क्वेश्चंस कैसे
Sorry,
सॉल्व
I can't hear you. Your voice is little down. I mean, Sandeep, can you
सर
please say louder little?
हेलो सर
Milan sir, he is actually asking how to prepare for CSI net topology, I think.
Okay, okay, okay. Topology, now a time you have to, with topology you have to need, what my knowledge says that you need also some concept of matrix space and some standard things, and you have to, main thing is that first complete this course. Okay, then try to solve problem of the last years. Okay, and solving problem will increase your strength. Okay, otherwise,
यस
I think there is no way to saying that particular say. But right now, those things right now, first to make sure that your basics is very clear. Basics. I think
यस
half of the course is on the basics. That should be very clear. After that, you will start to get a little little complex type of things, little little heavy things, and you will able to understand those heavy things from there. Just follow the rules, follow the line that has to complete lectures, and after that attend these tutorials, do assignments, submit assignments, do problems, little.
यस
So I mean, one thing, listen, one thing, that if you are not able to understand, right, solve a tough problem, you can try to solve a little easier problem. That will make sure that you will be able to solve the little tough problem. Okay.
यस यस सर
Okay.
थैंक यू यस
Okay,
थैंक
I'll stop here. Okay.
यू यस सर थैंक यू
Thank you. Thank you.